this first talk is going to be about splines. And I want to introduce splines to you not as some abstract mathematical concept, but as a very practical solution to a very practical problem that we run into in epidemiology or in exposure modeling. Okay? So the issue is, in our example that we've been studying, we want to know what is the effect of temperature on mortality rates in Chicago. And we are pretty confident that when it's very cold, mortality rates go up. And when it's very hot, mortality rates go up. So we think that the dose-response curve between temperature and daily deaths is going to be U-shaped. It's going to be high for very cold or very hot days, and it's going to have some minimum on nice days. So we need a way to fit that curve. And obviously, it's not linear. But I said it was U-shaped, so one possibility is to use a quadratic polynomial. And let's take a look at what this relationship might look like. So here's daily mortality and temperature in Chicago. It's high when it's cold, and when it's hot, it's low in nice spring and early fall days, and it's clearly not linear. But it looks like a quadratic polynomial could explain that quite well, because it looks fairly much like a parabola. Now, let's contrast that with this alternative scenario. Suppose indeed more people die when it's very cold and very hot in Chicago, but suppose instead of the simple parabola that I showed you, the relationship's a little more complex, so that starting from very nice days, there's a longer, slower rate of increase in deaths as it gets colder, whereas we get a sharper, steeper increase as it gets hotter. After all, there's no reason why the rates of increase should be the same. The physiological effects of heat and cold are quite distinct, and so the curves need not be the same. Can you fit this with a quadratic polynomial? I don't think so. Because a quadratic polynomial, if it's going up at that rate on that side, it wants to go up at the same rate on the other side. However, if I divide the range of temperature into two pieces, this is temperature getting colder and mortality increasing, temperature getting hotter and mortality increasing, then this half looks like half of a parabola. So I could fit a quadratic polynomial here in this part of the temperature range, and a different quadratic polynomial in the other part, the warm temperature part of the range of temperature. And in each case, I will do pretty well with a parabola, it looks like, but it won't be the same parabola. And so that seems like a reasonable solution to the problem. And that is exactly what a spline is. A spline is when you divide the range of exposure into two or sometimes more pieces, and you fit a separate polynomial in each piece. And it's nothing more complicated than that. And the reason you fit a separate polynomial in each piece is nothing more complicated than that the rate of increase in this piece and this piece need not be the same, and so you want to let there be different coefficients for the temperature terms in each side. However, there's one requirement that we generally place on splines. If I just took all the data less than this temperature and fit a quadratic polynomial for the cold days and did the same thing for the hot days, and they ignored each other, right? Then they're going to come into the nice temperature range, and there's no way, there's nothing that makes them meet up. So you're going to come in to this point where I've divided the range, and they're not going to be at the same level. And so the poor people, when it's 68 degrees Fahrenheit outside, are not going to know what rate at which they should die, because there seem to be two different answers. So we don't want to subject them to all that stress. So we would like to require that these curves meet up at that point. And that point is called a knot point because it's the point where we knot together the two lines so that they really do meet. Okay? And that's really all there is to splines. Now, I said polynomials. You fit a separate polynomial on each side. Polynomials, first of all, can be linear. I can have a piecewise linear spline. I could have a V shape, for example. Now, my guess is that's probably not going to fit the temperature mortality curve quite as well as having curves on each side, but it won't do a terrible job. And for some scenarios, piecewise linear polynomials will be perfectly adequate. Okay? Or the quadratic that we were talking about. And then you can march up the curve of higher and higher order terms. And any of those are available to you. You fit one polynomial on one side, one polynomial on the other side. You choose which polynomial you're going to use. You use the same degree on each side, however. Okay. Now let's talk about what this requirement that the curves meet up at the boundary point does. So if I'm on the left-hand side of the curve, so I'm looking at deaths as temperature gets colder, I fit a quadratic polynomial in temperature. I have a B1 times temperature. I have B2 times temperature squared. I do the same thing on the other side. For hot days, I have two different coefficients. Let's call them B3 and B4 for the right-hand side. Well, I've got 1, 2, 3, 4 coefficients. So it looks like I'm using 4 degrees of freedom. However, I'm requiring that the curves meet up at the boundary. Requirements use up degrees of freedom. In particular, if we want the curves to meet at the knot, then it turns out it must be true that the linear terms have the same coefficients on each side. That the only thing that changes is the coefficient of the quadratic term. So B3 equals B1. So now I only have 3 coefficients I'm estimating. B1, B2, and B4, because this is just B1 again. So I'm really using 3 degrees of freedom because I'm imposing the requirement that the curves meet up. So every knot reduces the degrees of freedom by 1. So if I decided to divide temperature into 3 ranges and fit a separate quadratic polynomial in each of the 3 segments, then I'd have 2, 4, 6 coefficients, quadratic polynomial in each piece, but I'd require 2 of the coefficients to be the same here and the same there, so that would reduce it to 4 coefficients. So basically, every additional division of the range of exposure, adding a new knot, adds another degree of freedom. So now let's take a look at a real example. I want to fit a model, not looking at Chicago and mortality. We've already done that in the lab. I want to look at Chicago temperature just versus time. So let me begin by looking at one season in 1 year. So here it is, April, May, June in Chicago in 2001, and this scatter plot is the temperature, which seems to be going up, and we like that. We prefer the temperatures start going up in the spring. People in Boston this year are really looking forward to that. Okay? And if you look at that, it looks like maybe you could fit a straight line to the data, and so I did that, and this is the least squares fit straight line. And you look at that, doesn't look too bad, right? But how do I know that that's good enough? So one of the things that we do when we fit curves to data is we want, including straight lines, is we want to look at the residuals and do some graphical diagnostics. And in particular, we think that the residuals should not be related to x or y. If the residuals are correlated with x, then you clearly didn't fit the right coefficient for x. And if they're correlated with y, you know, again, you must have done something wrong in fitting the model. And so we can look at how the residuals vary with exposure or outcome and look for various kinds of bad shapes or for outliers. So here is a plot of what happened when I fit that straight line to the data in the spring, where it looked like linear would probably do fine. Here is a plot of date, again, on the x-axis, but now I'm plotting not temperature, but the residuals of temperature. And, you know, at first glance, you say, well, you know, that doesn't look too bad. But all the residuals are positive in early April. And, you know, more of the residuals are negative here. And that suggests that maybe there's really some curvature in the relationship between temperature and date that we haven't quite fit. Now let's look at a full year. And so that would be an argument for using a spline. Now we look at a full year, and it's clear that a linear relationship isn't going to work, right? I mean, a linear relationship is going to wind up looking like that. That doesn't tell us anything. So what about a quadratic relationship? Maybe that wouldn't do so badly. So here's a quadratic fit through that data. And indeed, the quadratic fit doesn't do too badly, right? It seems to capture the up and down. However, if you look a little more carefully, and it's easier to do this with the residuals, but you can do it with the original plot, right? I mean, obviously, I have a problem there. There were some hot days in January. I mean, 10 degrees centigrade isn't so hot, but for Chicago, January, That's clearly unusual. And then I have the problem, right? This is the observed temperature, and the predicted temperature is almost always less than the observed temperature in July and August. So the quadratic polynomial is capturing the general pattern, but we've got some problems with the details. And here, when I look at residuals, it's even clearer that I have a problem here and that all the residuals are positive. The observed is higher than the predicted in the summer and early fall. So a quadratic polynomial isn't quite enough. And that suggests that maybe we need to do splines, divide the range of temperature up into maybe by season and fit a separate polynomial in each season, and we ought to do a lot better job. So I just suggested season. Why? Well, we associate different temperature ranges with different seasons, and so that seems somewhat natural, but, you know, maybe that's not optimal, right? And certainly, you know, April 1st may not be the optimal place to put a knot, right? So one of the questions that always comes up with doing splines is, how do you choose the knots? And where do you put them, and how many? Now, sometimes you use your sort of knowledge of what season is like. So, of course, people from San Diego don't have any intuition about that, so we won't trust them to fit splines to temperature. But for the rest of us, we have some idea of what's going on, and that might suggest, well, why don't I put knots at the beginning of each season, fit a quadratic polynomial in each season, and that ought to do a pretty good job. Maybe I could do a little better, but it should do fine. But that's not always the case. We don't always have prior knowledge. Now, in some cases, we don't have prior knowledge of season, but we have prior knowledge of physics or biology. So if I'm trying to fit some atmospheric phenomena and I know something about weather patterns, that may help me. Or if I understand something about how, you know, a biological variable is controlled, blood pressure, for example, that might help me. But sometimes I don't. And so in those cases, it's a little hard to decide how many knots and where to put them. So what can we do? Well, we need to be a little flexible, right? Sort of go with the flow. So what does that mean, and how do we do that? Well, let's come back to our temperature in Chicago over the course of 2001, and we could fit a spline to the data, and this spline looks like it does a pretty good job. We still have too many high points here, but this really looks like it was a very unusual event. And, you know, it's at the beginning of the data, at the extreme end of the data. We don't have any observations from the previous December to help us. And so it's not surprising we can't do perfectly there, but it does bend up a bit. And for the rest of the time, it seems to go pretty much through the middle of the data. So that suggests that splines are the answer to the question, how do I look at temperature over time? But it's possible to be too flexible. You know, Bertrand Russell once said that if your mind is too open, your brains will run out. That's true for data also. And we call that, in the case of data, overfitting. So here's the same Chicago data, and I fit a different spline to it, which uses more degrees of freedom. Now, on the one hand, it did a lot better there, right? It picked up those high temperatures in January. On the other hand, it's picking up what might well be just sort of random wiggles in the data. So if I really want to know, like, what's the pattern of temperature in Chicago, as opposed to what were, you know, spontaneous slight changes in weather patterns and stuff like that, I might be overfitting this curve. Indeed, if I fit this, and I want to use this curve as an example of the typical weather pattern in January, it is probably not typical to have very mild spring-like days in the beginning of January in Chicago. At least that's what my Chicago friends tell me. Okay? So maybe we don't want to fit that very well if we're trying to ask the question, what in general does seasonal temperature patterns look like in Chicago? So how do we fit the data pretty well but avoid overfitting when we don't have a good answer to how many knots and where to put them from our knowledge of the basic biology? Well, in some sense, the problem with this line is it's just too damn wiggly. So what I want to do is I want to limit how wiggly the lines can get. Okay? And the way I will do that, there are several ways. The way I'm going to show you today is something called a penalized spline. Okay? So let's talk about that. This is a way to deal with the situation where it's not clear to you how many degrees of freedom you want to use or where the right knot points ought to be. You do not have any confidence that the dose-response curve is linear, so you want to be flexible, and you want the computer to do something that makes sense for you. So how do we do that? Well, let's take a piecewise linear spline because it's easier to illustrate there, but this works for any polynomial, right? So imagine I'm back to looking at mortality versus temperature in Chicago. And we saw there was a U-shaped curve and it went up a little higher, perhaps in my hypothetical example, on one side than the other, right? Well, I can obviously approximate that with a piecewise linear curve if I have more pieces. I mean, to fit it with a piecewise quadratic polynomial, I thought it was good enough to divide into two different pieces and fit a quadratic curve on each piece. If I want to do a linear curve and still come close to what's going on, I'm going to need to divide the temperature range into more pieces, because straight lines approximate curves for a while, but not that far, and so I'll need more pieces. So I could have one piece there, and another piece there, and another there, and another there. So I have 1, 2, 3, 4, 5 pieces now, so that I can use a polynomial of lower degree, a polynomial of degree 1. And so I get 5 coefficients, right? And they're different in these different regions. Well, the bigger the difference is between B1 and B2, right? It's like this. If it was like that, then the curve would be more wiggly. So the bigger the difference between one coefficient and the next, the more wiggly the curve is. So I can define wiggliness to be a big change in the slope. And so I could take BI, the ith slope, minus the previous one, square it, because I don't want positive big changes and negative big changes to cancel out, because a sawtooth is wiggly. And so I square it and add that up, and that I can call a measure of the wiggliness of the curve. And if I divided it into 8 segments, right, instead of 5, it would be even wigglier in principle. It's going to tend to be wigglier because we have fewer observations in each interval as I slice temperature into finer and finer intervals. And that means that even if I can, in principle, well approximate the curve by a straight line, as the sample size within that interval goes down, my estimate of that slope of that line is going to get noisier and noisier. And I'm going to get variations just because of that noise. As the confidence interval for the slope gets bigger and bigger, the probability that the slope you got differs more from the true one goes up. And so you're going to tend to get wigglier curves. On the other hand, if there's more curvature, and I divide it into more pieces, I'm going to be more faithful to that curve, provided I had enough data to estimate in each of those pieces. So I have a trade-off. If I have more pieces, which means more degrees of freedom, I'm going to have the opportunity to be more faithful to what the true curve is, but the opportunity to have a lot of random noise making the curve wigglier than it really is. And so I would like the advantage of A, better fit to the greater curvature if it's really there, without the disadvantage, which is part B over here, which is my slopes start getting noisy and bouncing around. Okay? Well, so one solution is to penalize the spline for unnecessary roughness. You know, you run your hand over the sawtooth and it hurts. We don't want that. We want smoother curves, but we want them to be flexible enough to fit the real relationship. So I start off with enough knots so that I'm pretty confident that I can fit anything that's plausible. And then I penalize the curve for having the coefficients change too much as you go from one knot point to the next. So the slope in this segment can't, if it's very different from the slope in that segment, then this term is going to be a big number squared. It's going to be a big penalty. So if I estimate some roughness penalty this way, and then I have this, right? Because this gives me some penalty, right, depending on the change in the slopes, but I might want more or less penalty, right? I don't know how much penalty I should have, so I'm going to put in a tuning parameter. If lambda is big, it says, hey, get pretty smooth. If lambda is small, it says, wiggle around as much as you want. And then lambda is my volume control knob that's going to smooth out or rough up the curve, depending on how I turn it. And so I've reduced the problem of where to put the knots and how many knots to looking at only one thing, which is easier to solve than looking at two things, which is how big should lambda be? And I do that by putting in a lot of knots, calculating this penalty, and deciding how big it should be by turning the knob to make lambda bigger and smaller. So now I need to choose one thing, which is lambda, to determine my penalty. And of course, I also have to tell you how I'm going to use that penalty to actually constrain the coefficients so that these changes are not too big. So again, I use more than enough knots. I divide temperature into a bunch of ranges. The default in R is deciles of the data. You divide the temperature range into deciles, and there's separate polynomial in each decile. And if the relationship with mortality is more complicated than that, we're never going to find out what it looks like. So I've got 10 regions, and if I just did that, I just put in the spline with 10 different polynomials, I'm clearly going to get a curve that's too wiggly. Because I got 10 different polynomials. And that's where the roughness penalty comes in. If I constrain the coefficients so they can't change very much, that will obviously smooth out the curve, and I'll get something that looks more like that. How do I constrain the coefficients not to change too much? Well, that's interesting because there's supposed to be something there. So I want to minimize the sum of the squared errors plus R, which remember has that lambda in it. So if lambda is, so this is R. If lambda is big, then the penalty for having a big change in coefficients is going to be high, right? Now, if I change my coefficient more, I probably can fit the wiggles, even the random wiggles in the data, a little better. So my sum of squared errors will go down, but my penalty for wiggliness goes up. So there's a trade-off, and there's going to be some optimum, which is going to minimize those two. And as lambda gets larger, that optimum changes to give you a smoother curve, because the penalty for changing the coefficients is getting bigger, and the optimum will occur with smaller changes in the coefficients, less wiggly curves. And so that's the idea of a penalized spline, and I still haven't told you how we're going to choose lambda. But I have told you how choosing lambda in fact works to tune the curve to be wigglier or smoother. Sorry. And so this is called the penalty term. Well, one way to choose lambda is to say, I'm trying to predict what's going on, the true relationship between temperature and mortality. Why don't I have a validation data set? And then, if I have a left out data set, which is Chicago in an alternate universe, because there are an infinite number of alternate universes, and I just look at that other Chicago where the temperature by chance happened to be different, right? You know, I can make predictions there and see how well it works, right? Or maybe I look at another year in Chicago or something like that, but let's say I have a validation data set. So I fit a curve for mortality versus temperature in my training data set, which is Chicago in 2001. Okay, and I get a curve, and I find that it looks like that, right? I take the predicted mortality at every temperature from this curve, and I go in the validation data set, and I say, oh, well, 22 degrees, bingo, that's my prediction for how many people died on that day. And then in my validation data set, I have how many people really died on that day. And I add up the sum of the squares of the prediction error. And that's a measure of how reliable the prediction was. Now, suppose I have turned up lambda so that I fit a curve that was smoother. It looked like this. And suppose the green curve were the truth. Then I'm under-predicting mortality here, I'm over-predicting mortality there. If the green curve is the truth, then this smoother curve will have bigger prediction errors. And so the sum of the squared prediction errors in the validation data set will be larger. On the other hand, suppose I turn down lambda, the lambda dial, so I have very little penalty, and I wind up with a curve that looks like that. Much wigglier. Well, compared to the green curve, guess what? This curve is also over-predicting mortality and under-predicting mortality. And even here where they're going around, you know, I have this downward wiggle, which isn't really there in truth, followed by an upward wiggle, which isn't there in truth. I have a bump here, which isn't there in truth, because truth is the green line. Remember that. Okay? So my prediction error will be larger if lambda is too small. It will be larger if lambda is too big. And choosing the lambda that minimizes the sum of squared prediction errors finds the lambda that's not too hot and not too cold. And that's what we want. And so that's how we do it. Now, what if you don't have a validation data set? We still want to do that. We're just going to have to be a little cleverer about it. So this is basically a summary of what I said before. I predict the outcome in the second data set using the equation the curve from the first data set. If the model is too smooth or too wiggly, I get more bias and I get bigger predicted errors. Now, if I don't have a validation data set, I need to construct one. And here's how we do that. So I could leave out observation 1, January 1st, 2001, fit the model to all the other data in Chicago, predict, given the temperature on January 1st that actually occurred, how many deaths my model predicts will occur on that day, compare that to how many really occurred, square that. Put observation 1 back in, take out observation 2. Fit my spline with the given value of lambda, predict how many people die on January 2nd, compare it to how many really died, square that. Keep doing that through the whole year. I get 365 sum of squared errors. That's how bad my prediction is for that choice of lambda. Do that for a range of lambdas, and I can see that its prediction error is going down if I move lambda in one direction until it turns around and starts going back up. And so that bottom point where the predicted squared error is minimum, that's the lambda to choose. It's not too wiggly, because if it were, you would predict wiggles that aren't there in the validation data set, but it's not too smooth. And so that's how penalized splines work.